咱们期末考试，对，就其中最后的是，对，偏序和考偏序，还有这个
你说 quiz 啊？
不是，
那是 quiz
那个 quiz，
啊
我们干到一个啥，
，final 是从期中之后。
所有的
下周才考。
下周考，
就是考那个 partial ordering diagram，partial ordering diagram。
就考这个吗？graph 主要的，
对，hello hello 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 can hear interesting Next one too. Testing. Gia Hui, Gia Hui, Gia Hui, Gia Hui. Yeah, yeah, yeah. Okay, let's close the door behind. Okay, hopefully everyone here. Maybe at least someone joined from maybe my video comment. Okay, before we start, some announcement. So we have some of you keep asking me about the quiz. So we will have the quiz next week. Combine quiz 4 and quiz 5 together. So worth about 20 marks and 8% of your continuous assessment. And the scope will be start from partial ordering up to graph. Okay, partial ordering up to graph. And make sure you know how to draw the Hessel diagram. So we will use Hessel diagram as a graph, and then we'll check the property of graph of Hessel diagram. Today, during the tutorial, we will discuss about quiz 3 as well. Okay, because last week we discussed about midterm, so this week we discussed about quiz 3. And then I also did some correction to my lecture 9 and 11. You should read again. You should read my lecture notes together with your textbook. Is the best combination. But I'll still keep updating and then repair my notes. Okay, but don't just read my notes, okay? Because some of it I didn't, how to say, for some of the proof I didn't write it in detail. I just write the main point so that you can understand it in the book. Okay, I try not to put all the things into my notes, otherwise it becomes another textbook, which is very hard to follow, I think. But at least I need to make it self-contained, so that when you read it, you know what happened. Okay. Any question from you? Question from you? Hopefully today we will have more time for tutorial. I think you did receive my email, right? Did you? Okay, my announcement. So hopefully by planning we will finish the syllabus next week. If we manage to finish next week, then the final week we will do summary and maybe go through as much tutorial question as you like, as detailed as you like. Okay. So make sure you gather enough question to ask or to revise on the last week. We have the exam on the which day? When's the final exam? Thursday? Is it Thursday? First week is it? Or Wednesday? Tuesday? Tuesday. Oh, Tuesday, okay. Tuesday first week. Tuesday or Wednesday? Wednesday, okay, yeah, Wednesday. Second day of the exam. Okay. So we should have enough time to do revision 1 week. Okay. I promise you will be easy this time, okay? Okay. Okay, let's recap what we did last time. Okay, today I think I will write less, so we will just go through some slide and then I explain the algorithm. Mostly today will be about algorithms or finding different objects. Okay, so let me remind you what we did a few weeks ago up to this week. So we spent a lot of time looking at diagram graph, which we call graph. Look at graph, property of graph, how we color the graph, or any Euler path, Euler circuit, Hamilton path, Hamilton circuit passes through the edge once, or passes through every vertex once. Okay. And now we move on to look at a special graph. Okay, which we don't want to look at the graph that contains simple circuit. So that means we need to remove this kind of remove edge that can form circuit, which is connected, non-simple circuit, and that's all. So this is what we call trees. Okay. So in trees, we consider the rooted trees. Okay. Rooted trees where you start with a root, okay, and then you can rearrange all other vertex that is directed away from the root. For example, this one is a root. So we have this. Okay. And then we create a lot of terminology like parents, ancestor, descendant, leaves, internal vertex, okay, to describe where's the position of the vertex. Okay, so you can think of it as a family trees. And then if you, what's the application of this graph? So if you replace the vertex with atom, okay, if you learn chemistry, you can see this kind of uh, chemical substances, okay, where C is the carbon atom and H is the hydrogen atom. Okay. And then what else? You can do it as an organization tree. For example, organization for the university, for the school. I think even for your student society, you also got it. President, secretary, treasurer, and then committee. And also computer, you can have different files entry, right? You also can form the trees. Okay. When you use the computer, you can go into this file and then go into the next file. And then you can form a tree as well. Okay. I hope you are familiar with this. I'm not. Okay. This is the what is this? The it's, what do you call this? Just call it entry, files entry. Is it? So this one. There's like .bin or what? Inside your computer file, right? The Windows, you will see a lot. Users and then what? Okay. The entries, directory of your files. Leaf are the files, and then internal vertex are the directory. Okay. So mostly we were interested in rooted tree for now. From now on. So we will continue to introduce some terminology. For example, we call a tree Emery tree. Okay. Emeries actually start from binary. So let me draw something. So if the tree for all the internal vertex, you have two child, at least at most two child, we will call it a binary tree. Okay. So Emery tree will have no more than n children. Okay. This one is a binary. If it has no more than every interval vertex has no more than two child, we call it a binary tree. If no more than n child, we call it m children, we call it a Emery tree. Okay. If every internal vertex has exactly m children, then we will call it a full Emery tree. So in this case, this one is a full. So something that is not full binary tree will be something like is a binary tree, but uh, okay. Okay. Next. And here. One more, two more. Eh, full one. Okay. Okay with Emery tree, full Emery tree, binary tree. Okay. So this is just terminology, not very important. Okay, next. Oh, later we will formulate some theorem, simple theorem. Okay, next one is the ordered rooted tree. So when you draw the rooted trees, okay, we want to order the children. Okay, if it is, we will order the children from left to right. Okay, so we will order the children from left to right. So for example, like this. Okay, the children will be ordered from left to right. So and then so the left one, so the first child we call the left child, the second child we call the right child. Okay, for in the binary trees. So in binary trees, okay, so in binary trees, how many leaf how many children do you have for every internal vertex for binary tree? Ah, how many children do you have for each internal vertex? Two. At most two, okay? At most. At most. So the left one we call the left child, and then the right one we call the right child. The first one we call the left child, the second one we call the right child. First left child, right child. Okay. This is just terminology. So the tree rooted at the left child of a vertex is called a left subtree. So if you got a left child, okay, and then you got a subtree below it, you call it a left subtree. Okay. So you can consider the whole tree below the left or right child. If it is right, then you call it a right subtree. This terminology will come apparent when you want to discuss about tree. Okay, next one is a theorem. A tree with n vertexes has n minus 1 edges. Okay, so if you got a tree and then you got an n vertex, you must have n minus 1 edge. Is it clear why? Is it clear why? So for example, if you have one tree, if a tree with a one vertex, then you don't have an edge. Because if you got a head, what do you have? You will have a loop. A loop is a circuit. Okay, so you don't want simple circuit. So how about if you have two vertex, then you have one edge to connect them. So you got a connected graph. Okay. If you have more than one, what do you get? You get either double uh, multiple edge or you get a loop. Okay. But it's a connected simple graph. So this one on the right. Summary. So it can be proved by induction and also refer to definition. Okay, next, a full memory tree. So meaning every internal vertex has exactly how many children? Memory trees. So memory tree, full memory tree, every internal vertex has exactly m children. Okay. If you have m children, okay, m children with I internal vertexes. Okay. So that's mean you got like m children. Okay, every vertex of m children. Okay. And then you got I internal vertexes. So for example, this kind of so every vertex with you have let me go first. So you got I vertex. Okay. So the sum of blue blue vertex being this Can I write like that? Okay. Okay. So I internal vertex means there are I vertex with M child, right? Realm. Ah, wait. So what's internal vertex? Internal vertexes are vertexes with children. Okay. So how many children each vertex has? Huh? M, right? Two memory trees. Okay. So every vertex has M children. So M times 1, Y plus 1, because you need to add your root. Too fast. Wait. Um. Wait. Okay. Again. So again. So the question is, a full memory trees, okay, contains how many vertex? Okay. Correct. Right. Okay. So now it tells you that a full memory tree has I internal vertex. Okay. Meaning you have I vertex which has children. How many children each of them have? M, because you are full memory. So every parents, you know, that they have M child. Okay. So M times I plus 1. Why you need to plus 1? Because you need to add your root. Yeah. M times, yeah. Okay. So yeah. 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 Shouldn't be too difficult. I mean, don't know why the projector not working. Restart it. Projector not working. Not working. Hello? Projector not working. Sorry? It's on, but not sure why not connected. Not sure why it's not connected. Sorry? Using HDMI. 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 Uh, don't have VGA port. Only have HDMI port, but only showing blue screen. Start my laptop. Hey.啊，还考一看。哎，这种电器的东西是这样的，你关心它就出来了，不关心它就不出来。对，不知道吗？哦，right leg，leg 哦。Okay, okay. So let's come back. So recall that we said that the number of vertex is partitioned by the number of internal vertex and the number of the leaf. Okay, because every vertex either have a children or you don't have a children. Okay, so the number n is equal to the sum of I internal vertex plus L number of leaf. Okay, so let me write down n equals to I plus L. Okay, so from this formula you can deduce the following. So if you have a full memory tree with n vertex, then you can get the internal vertex is n minus I divided by m. I think this one not hard to see, right? Because this is just the manipulation of the formula just now. N equals to mi plus 1. So you just move I as n to the other side, right? Remember just now. Okay. And then if you want to count the leaf, leaf is just what? N minus I. Okay. N minus this number here. Okay. Don't be scared. Don't be frightened by this formula here. This is just playing around with these two formula here. Okay. And then you can play around more. Okay. You can get 2 and 3. If you fix I, and then you can go and find your N, and then find the L using these two formulas. So what I should say here is proof use to im plus 1 and n equals to I. Okay. So maybe you ask again, so what's the use of this theorem? Okay, I think the textbook figure out for you. So should I go through this example here? Yes. Okay. So okay. So so okay. So the question read like this. Suppose that someone starts at a chain letter. So what's the chain letter? So let's read what the chain letter is. Each person who received the letter is asked to send it on to four other people. Okay, so once you receive it, you send to four other people. Some people do it and some people didn't do it. Okay, like usual. Okay, people don't. Okay, how many people have seen the letter, including the first person, if no one received more than one letter, and if the chain letter ends after there have been 100 people who read it but did not send it out? How many people sent out the letter? Okay, so uh, so he asked how many people have seen the letter, okay, including the first person. So that's mean the root. If okay, if no one received more than one letter, okay, if no one received more than one letter, if no one received more than one letter, and if the chain letter ends after there have been 100 people who read it but did not send it out. So 100 people is the leaf. Read it but did not send it out. Okay. Internal vertex is the one who read it and send out the letter. Okay. So the claim is from this number you can check how many people that has sent out the letter. And also how many people have seen the letter. Just by knowing how many leaf. Okay. Yeah. You can read your solution yourself or not. So the key is like you only have how many? I think you only have two. Okay, I only have two piece of information, but you can know how many people read it and how many people actually send out the letter. So you can get the also. So what information you have? You have two memory trees. Okay, you have the number of M. You also have the number of leaf, and then you can get the internal vertex and also the vertex. How many people send out the letter? So who are there? They are the internal vertex, and then what else? Don't remember have seen the tree is the vertex. So you got the. Do you want me to write down? Okay, I write down. So okay, so only you have the. Okay, I summarize this for you. So info you got is two, three. Okay, so you know that everyone must send to four. Okay, so I think this is the usual instruction you will get. So in this case, M is equal to 4. And then 2 is leaf, right? So leaf is equal to 100. Okay. So leaf means in this case you read it. uh, Okay, so you don't have children. So info, so uh, achieve, so is the target. So what you get is you get uh, the number of vertex, texes. Okay. So number of vertex is in this case is number of people in the, okay, and then second is the number of internal vertex. In this case will be number of people that read but didn't send the letter. Okay, so 2 pieces of information you can get another 2 pieces. You don't need more than 2 pieces. Just 2 pieces of information is enough to recover the whole system. Okay, but this one only works for 3. Huh? Okay. Huh? Sorry, should send a letter, right? Okay. Yeah, but send the letter. Leave is didn't send, so yeah. Leave send but internal vertex. Leave didn't send but internal vertex send the letter. Yeah. Okay. This is just some application. Okay, next is the level. So for the level is the length from the root to the vertex. So if the root start from level 0, okay, and then the child of root will be at level 1 because path length is 1, and then the level 2 will be the child of the grandchild of the root. Grandchild is my invention, sorry. Then great grandchild. Okay, that one is just my invention. You see this thing again. Four, 4, 3. Maybe we can take a break to 4, 5, 3. Yes, take a break. 走吧，下来做。你都有问题耶。Hello， hello。Cable got problem。好高的东西。Hello, I think cable got problem. Cable got problem. Cable got problem. Hello. 真是糟糕，是吧？那个他刚才那个这个是那个，他不一定是管自己说什么？为什么能够直接用这个性质？是不是那个性质特指死不还是可以？哦，定盲，这哎对对，给我3个啊，所以上面这种不满也可以，给我3个，一定要满，这个是说满的，这个满不满？这一部分，看看啊。哦，可能是哦，他一
读了过后，他一定要发给4个人吧？就是他是他不发
他只有不发和发4个
啊
对
啊，
但是这也不是嘛，不一定嘛，它可以换成这也不是嘛，就是
有些
比如第2层它就
可以发给不发，给发给4个人。
分版的意义不一样。
没有，对，可以啊，可以啊，为什么不可以？就你看啊，可以再加多一个，他就他如果发，他就发4个人嘛，对不对？
对，然后可能
发要吗？
对这2个人没发，就这样。
这个也是也是负啊，
这是负，
这是负，
这不是
你说的那个是这个是吗？
那不是要全部？
全部你是说这个哈？
对
这个还有另外一个，它叫做 complete
啊，完全
啊，
完全说的不是，
这是 complete
那完全是
啊？
不是，我再画另外一个，
哪个？
还有另外一种，
你画
这样的，
他来了吗？哪一种？
这样的，它不也是完全？
啊，这个不是完全，
这是完
这个叫做 theory，OK，然后如果我有加这一条，
这
就变成负
这不加，现在就是完全
啊，
它叫完全二叉树
啊，你存在。加了这一个就变负了，因为每一个 internal vertex 都有2个桥，然后
不加的话
啊，
它叫完全，
不加没有，
叫完全，
不加叫这个，
就是只要满足这一层，它
只要每一个都有至少2个孩子都最多2个，就叫做负对 and most 吗？
但是这里谁说每个那一点都要相合？
OK， oh using converter, but this one need to fix 什么 later you fix OK you fix later OK thank you and next week also go
是
this one yeah
这个是之前的
you can lock
理解，他这么讲，我就这个，B 选项它为什么是啊？它好像没有 transition。
Later this conversion after you finish
OK 等一下我看
after you finish this converter you just give it back to our office at 2:30
I finish 7 o'clock 啊
tomorrow
啊 OK tomorrow OK 7几天
老师，B 选项为什么是偏虚啊？好像找不到 transition。
说它不 transitive 啊
我觉得它没有 transition。对，我觉得它
有 transitive 你要我现在说
有意思。后面会说吗？
我可以解释一下
嗯
好等一下 tutorial 讨论会上我讨论这些
嗯，
OK 提醒我一下我
好的。
那个谁再说一场
啊
就是 every internal birthday。
对这是 full 对 every 的对
那像要是像刚才就不是负，
哪个这个
就不是这个擦掉，就不是
没有啊它这个不是 internal vertex 这个是 leaf 啊对没关系
leaf 不是。
对
那看这个定义，
哪个
百度上说它是完全二叉树。
等一下啊我调一下不要这个另外一个对这样哪个
他说这个是完全二叉
你看有完全有满的，
对啊，这个是完全二叉树，然后满二叉树是完全二叉树的特殊形态。
标记什么东西？
嗯，
它没有标记还是满还是什么？
那它是完全，它这个定义是这样的。对满二叉树的节点进行编号，然后当如果1到 n 节点都对应，就称之为完全，就是右边的点少。
可以有英语啊？
啊，
有英语啊？
百度应该没有吧？没有吧？
等下那个头，你的课本不是有吗？课本不是有吗？
会不会有这种？
有啊，课本有。怎样？还有2分钟，有吗？不知道你们是要指敷啊，还是要指 complete？我没有介绍 complete 啊。非常。Hello, testing. Okay, let's come back. Maybe I'll sit here. The cable got problem again. If you want to see me, just call me. Okay. Okay. So just now we talk about level, right? Okay. Next we talk about height. Okay. Hello. Come back. Okay. Next is about height. Okay. Height is the maximum level of the vertex. So in the example just now, we have the height is equal to 3. So in other words, the height of the rooted tree is the length of the longest path from the root to any vertex. Okay. So the longest path is from 0 all the way to vertex in the level 3. Okay. Level and root. So one thing to note here is the level of your root is 0. Okay. I think some of you maybe you will start from 1, but make sure you start from 0. Level of the root is 0. 0, 1, 2, 3. Okay. If you start wrong, then you will have extra 1. Okay. Next thing is about balance. Okay. Whether the tree is balanced or not. Okay. A rooted emery tree of height h is balanced if all the leaves are at level h or h minus 1. Okay. You cannot differ more than 1. Okay. If we are just around h or 1, that's fine. Okay. If we have leaf at 2, then that one is imbalanced. Okay. Maybe you will fall down. Oh. Yeah. Okay. So as long as all the leaf is h or h minus 1, okay. If h minus 2, then you are imbalanced. So you will fall down. Okay. Yeah, that's all. Okay, next. Okay, now it's the algorithm. There are 4 algorithms here you have to learn. Okay, 4 algorithms you need to learn. So now we will talk about tree traversal. Okay, traversal. So meaning we want to go over all the vertex of the tree. Okay, how to go over the vertex systematically. Okay, this is what this subject or this topic here. How to go over every vertex without mixing them. Okay, so first we call it a universal address system. Okay, so you name the root 1, you name the child of the root 1, 2, 3, 4, 5. Okay, you see them as a ordered rooted tree. So you see the child, order the child from left to right. Okay, 0 and then 1, 2, 3, 4, 5. And then the child of 1, you put 1.1, 1.2, 1.3. Okay, let's say you got a child of 1.1. Okay, what do? You name it 1.1.1 and then 1.1.2 and then so on. Okay, do it for all the trees. Okay, so how you label, how you order them. Okay, so you start from 0. Okay, and then 0 is less than 1, 1 is less than 1.1. Okay, 1.1 is less than 1.1.1, and then 1.1.1 is less than 1.1.2, and then 1.1.2 is less than 1.2. So you go over the tree first, and then you go to a different subtrees, and different subtrees, and this one. Okay, make sense or not? Make sense, huh? This one makes sense? Okay. Okay, so this algorithm, we call it a transversal algorithm, okay? So systematically visiting every vertex. The next one is called a pre-order transversal. Okay, this one very important. Exam got. So pre-order transversal. Okay. So how to read this tree? How to arrange order the vertex using pre-order? So pre-order means if, okay, so the algorithm is like this. So first step, if your T only got one root, okay, then you read it as R. Next, if your tree got T1 up to Tn sub trees, okay, from left to right. So you need to first visit R first. Okay, you visit R and then you visit trees on the left. And then tree on the right. And so on. Okay, so how this goes, okay? Let me show you how this goes, okay? So first step you need to remember is visit the root first, and then traverse the left subtree, and then traverse the right subtree. Okay, so let me show you how it works. So example, this is the tree. Okay, so you need to visit the root first. Okay, so you visit the root first. So you visit the root first. Okay, so you start with the root, and then you need to visit the tree. Okay, visit the tree. Left subtree and right subtree. Okay, let me label it. This one is the left. This one is the right. Okay, you should imagine there's more subtree going on, right? So also left to right. Okay, so now only got 2. And then when you traverse this subtree, okay, visit the root again. Okay, visit the root again, and then transverse the left subtree and the right subtree. Okay, so every time start with a root, and then left subtree, right subtree, root, left subtree, right subtree, and then root, left subtree, right subtree. Okay, so what we get here is A, and then left subtree, you transverse it, you get the root of the left subtree, and then you transverse the left subtree and the right subtree. So it's a E, F, then, and then the left subtree and right subtree. So C. Okay. So in this way, you systematically transverse all the vertex. Need to repeat or not? Or any part you confuse? No? Okay. 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 So far, okay. Okay. So you can see that there are 3 steps of this step, right? 3 of this step. Okay. So we can permute these 3 steps. Okay. Okay, I don't give you the full definition here. You can go and check your textbook if you want to see a full definition. But I just summarize for you. And then you go and check, read it, see measures up. Okay. So the next one we introduce is in order and post order. Okay. Correspond to 3 permutation of this this step here. So in order means you put the visit the root in the middle. Okay, so you read the left subtree first, and then you visit the root, and then you read the right subtree. This is called the in order. Okay, if you put the visit the root at last, it's called the post order. Okay, so post order means transverse the left first, transverse the right, and then visit the root. So you can see this. Okay, one pre-order is visit the root first, and then left, transverse the left, transverse the right. Okay, in order means transverse the left first. Okay, go back to the root, and then transverse the right. Okay, so these 3 is concerning when you visit the root. Okay, so post order means you visit the root last. So you transverse left first, transverse right, and then visit the root. Okay, let's see what's the difference. Okay, see what's the difference. Okay, for example, in order transversal. Okay, so in order transversal for this case here. Okay, so we need to transverse the left first, visit the root, and then transverse the right. Correct? Follow? Everyone follow? Follow? Okay. So to transverse the left subtree, you need to transverse the left subtree, visit the root, and then transverse the right. So what you get is E, B, F, A, C. Okay. Can? Following? Following? Okay. So the next one, okay, if you still not follow, try to follow this post order transversal. So post order transversal say you transverse the left first, do 2 first, and then transverse the right 3, and then visit the root. Okay. So you transverse the left, transverse the right, visit the root. Okay. So when you transverse the left, you need to transverse the left, transverse the right, and then visit the root. Okay. So what you get is E, F, D. After you transverse the left subtree, you transverse the right subtree, and then you visit the root. Okay. Any question? If no, later we try a longer example in your textbook one. Any question for now? Any question?
So if you start with
Ah.
the left subtree, I think,
Yeah.
then we go to the lowest one.
Yes.
Lowest one.
I mean, because yeah, because when you transverse the left subtree, okay. So when you transverse the left subtree, okay, because when we define the yeah, so when we define the transverse, right? Yeah, how should we let me check. So we only define, you see, we only define it for the tree has one vertex. So every time when you visit the subtree, you need to reduce the subtree to one vertex. Then you can start take out the vertex. You get what I mean? You see the definition here. If T consists of only R, then R is the in order transversal. This statement here appears for every transversal, every order transversal. This is for only one point. Okay. The key is when you have n subtrees, what do you do first? You visit the root first, or you transverse the left subtree first, or you transverse the right subtree first? Okay, which one you do first? So you want to take the middle one out first, or you want to take the leftmost out, or you want to take the rightmost? Okay, no, not rightmost, but yeah. Okay. Yeah. So every time you got the tree, you have to keep reducing until you only have a subtree with one vertex. Okay. Yeah.
Okay. Here. Maybe we try another example here then. Yeah, let's try this example here. Okay. So ordered tree here, okay, pre-ordered. So pre-order, what first thing you need to do? What's the first step? Visit root first. Where? Left sub tree. Okay, transverse left sub tree. Left sub tree. And then transverse right. Right sub. Okay. Okay, so what do you do is you can see that here got a root, here got a left sub tree, right sub tree, right sub tree. Okay. Okay. So you visit root first. So you put down A. Okay, you put A. Okay. And then you need to transverse your left subtree first. Okay. So to transverse left subtree, you need to visit root and then transverse left subtree. So what you get is A, B. Okay. So to transverse left subtree, you need to visit the root first. So you get A, B, E. Okay. And then after you visit the root, you do what? Transverse the left subtree, J. Okay. After you do the left subtree, what do? You do the right subtree. So when you transfer the right subtree, you visit the root. Okay, and then you transfer the left subtree. And then you transfer the right subtree. And then you transfer the right subtree because right subtree all are root. Right. Okay. So after you transverse the left subtree, you transverse the left subtree. So left subtree is only root. So and then you finish this subtree, you go to the right subtree. Right? Right. This subtree already finished, huh?
From P to F.
From P to F. Oh, from P to F is after you transverse this left subtree, you go to the right subtree. So you transverse all the left subtree, you go to the right subtree. Okay. And then you transverse this left subtree, you transverse the right subtree. And then you transfer the right subtree, you need to transverse the left subtree. I know. Say until you memorize. Okay. C, and then what you do? D, and then G, L, M, H, I. Okay. So let's check the answer. Yeah, let's see. A, B, E, J, K, N, O, P, F, C, D, G, L, M, H, S. Okay. All right. Okay. So you want to go through the in order transversal yourself, or you want to go through together? Huh? You want to do yourself, or you want to go through together? Yourself, huh? In order. Post order also can go through yourself. Huh? Same thing, huh? Okay, I think algorithm is easy for you guys. Okay. Yeah, and then one thing very interesting one is all these three pattern here, right? You can do using this following this line here. You can read about it. I don't want to explain, but you can read about it. If you do many, do a lot, do enough, you can see this pattern. Okay. No need to explain. In order and post order. No need to do example. Oh, good. Good or not? SWE cannot answer. DMT only. DMT. You want one example for in order or post order or not? You want to do one more example or you are fine with it? DMT. Huh? Okay. Do you want more example or no need? No need. No need. This one confirm I tell you got come out in exam. You must master this.
All these three. All these three.
I mean this subject. Okay. Okay, if not, maybe you can leave to next week if you want to check with me. Okay, next is about another algorithm. We want to find a spanning tree.
Okay, so what's a spanning tree? So spanning tree, you can think of it like a backbone. Okay, backbone of the graph. Okay, so what's the backbone of the graph? So if you got a graph, okay, a spanning tree is a tree that contains every vertex of the graph. Okay, so let us see the graph here. So what's an example of spanning tree? So first you need to have all the vertex. Okay, so you need to have all the vertex. And then it is a tree. Okay, it is a tree. So how can you draw it? So maybe you can get this tree here. Okay, so this is a spanning graph. Or you can pick a different one. Maybe you can pick this one. Seems like not clear. Or maybe it's this. Okay, you also can pick this. Yeah, you also can pick this. Okay. So it's like backbone of your graph. Okay. Make sure every vertex is connected, but it's still a tree. It's a tree, yeah. It's a tree, no simple circuit. Okay. If your bonds form a simple circuit, then you form a loop, right? Okay. So a theorem, a simple graph is connected if and only if it has a spanning tree. I think we won't prove this. So what this means is, if your graph is connected, you can find a spanning tree. Because it's connected, right? So you can find a spanning tree because you can connect all the vertex. If you got the spanning tree, if the graph got a spanning tree, then it is connected. Yeah, because spanning tree already tell you, already connect all the vertex for you. Yeah, okay. So this one to be simple. Okay. So next is the algorithm for finding the spanning trees. Yeah. So the algorithm to find this purple or the green line. Okay. So first one is the depth first search. Okay. So later you will know why is it called depth first search. Okay. So we grow more depth first. Okay. We grow more depth first. So this means we pick a vertex. Okay. We pick a vertex as a root, and then we form a path by adding vertex as long as possible. Okay. And then if you haven't formed a spanning tree, go back to the previous vertex and then grow again. Okay, show you an example. Okay. So let's say you start with G. Okay, we follow this example. If it is not enough, then I show different route and then show you what's the pattern. So first you start with G, okay? G is not 3 yet, right? Because this is a simple circuit. Okay. So maybe I start with F first. So we start with F and then we grow. So we grow from G, H, K, J. Okay. And then done, finished. But we haven't finished all the vertex yet. So we need to go back to the previous one that still can, am I saying it right? So you go back to the next one, which you haven't approached yet. Okay. So like you go back to H and then go to J again. Okay. So from H you have children. So I become a children of H. Okay. And then from F, you haven't go to this side yet, right? So you need to go back all the way back to F and then move to either E or D. Okay. So in this case, they move to D. So we move to D first. Okay. And then move to D, we can move to E, move to C, and then they go to A. Okay. But you haven't reached B, so you need to come back from A, and then you go from C, you go to D. Make sense of? So you return to the last vertex, which is adjacent to the vertex that is not yet visited. one more example for this. You want one more example for this? Okay, which vertex you want to start? That's me. So which vertex you want to start? Let's see what A, yeah. Okay, let's start with A, yeah. Okay. So let's start with A. So we keep growing the so form a path by adding vertex and edges as long as possible that's adjacent from A. Okay. So A we can go to C. Okay. Maybe let's go to B first. Okay, we go to B. Okay. Then is it a spanning tree? No, because we haven't reached all the vertex. So we need to return to the vertex for the last vertex that is adjacent to the vertex that we haven't visit. So we go back to C and then we move to E. Okay, move to E and then we can move to D. Okay, and then we can move to F and then we can move to G and then we can move to H. Okay, and then we can move to, for example, we can move to I. Okay. Okay. Let's say after we move to I, is it a spanning tree? Not yet, right? Because we haven't reached K and J yet. So we have to move back to the last vertex, which is adjacent to a vertex that is not yet visited. So we have to move back to H and then grow to K and then grow to J. Yeah, this one is being calculated. Should be like this. I, J, K. Okay. So this one got a level. So we got like 0, 1, 2, 3, 4, 5, 6, 7, 8. Level 8. But this one is level 1, 2, 3. Okay. So this one can grow as long, quite long. Quite long. Okay, so far okay. We're good with this. Okay, the next one is the breadth first search. Not breadth first, it's a breadth first. Okay. So breadth meaning wide. This now is deep. Now it's wide. So how do you grow as wide as possible? So as long as the vertex is incident to the vertex is adjacent to the other the vertex, you just add them first. Yeah. So what this means is you add all the edges that is incident to the root. Okay. And then you keep doing it. Yeah. So for example, in this case here, okay. So in this case, we start with E. Okay. We add all the edges incident to this. Okay. So that's mean right. We add D, B, F, I. Okay. And then the next step from D, B, F, I, we add B, we add A and C. Okay. And then D, we add H. Okay. So there's one point to add here. Why not I add D to A? D is also connected to A. Why not I add this? Why don't I add this? Why? Why? Why not I add A here? What happens if I add A here? D, A, H. What happened? What happened? Anyone know? D is connected to A, right? So why don't I add D to A? Anyone know? Huh? What? Yeah, so why can't I add another H here?
It's not free.
Yeah, so if you add D to A, then you can form a simple circuit, which is not a tree anymore. Yes, that's right. So you can either add A here or you either add A here, but you can't form a circuit. Yeah. So in this algorithm, actually, you need to avoid circuit, you see, without producing a simple circuit. Okay? You need to avoid circuit. Okay. So in this case here, you will have a breadth-first circuit. How about let us try this? Okay. Let's try the breadth-first. Breadth-first here. Breadth-first. We also start from H. See what we got. Okay. So we start from H. We use the breadth-first search. So start from H. So we add all the edges that is incident to it. Okay. So we got what? We got E. We got G. We got H. Okay. And then start from E, we can connect D and C again. Okay, so it's D and maybe put here C and D. G, what do we have? We have H, but we don't want to have simple circuit. Okay, no need to connect anymore. So we need to do H. H is connected to I and K, and then no need to go F anymore because we already connected. So we will have I and K. Okay, and let's start from C. Okay, who are edges incident to C, edges incident to C, which is A, and connecting A and B. D is F we already have, so we cannot have a simple circuit. And then F got F, E, A got I got I last one, K joined to J. Okay, so you see what's the level of it? 0, 1, 2, 3. But here is level 4. Here is level 3. But this one, the breadth is larger because here only got 2. Okay, so here, focus on that. One is focus on. Okay. Same root, different trees. Okay, both of them are spanning trees. Okay, spanning tree for this graph here. Okay, so different algorithm will produce different thing, but pick your. Okay, very good. 523. Okay, next is what we call a minimum tree, minimum spanning tree. Okay, so what's the minimum spanning tree? So now we are considering this weighted graph. So the edges we got number. When you move along the path, you will add up. Move along the edges, you will add up the weight. Okay. So what's the smallest possible sum of weight of x edges? Okay. Can get it or not? So you find the spanning tree, okay, that have the smallest possible sum of weight of all the edges. Okay. Huh? What is weight? Huh? Okay. So remember we talked about multiplicity of the edge. Okay. So on the edge, we can put like number multiplicity, or in this case we call it a weight. Okay. So for example, like this edge here can have different number. Okay. Right. So now we want to find a spanning tree. When you add up the sum here, it is the least sum. You get it? Huh? Wait. No. Weight of the x is this number, the label of the edge. Yeah, label of the edge. Okay. Or the multiplicity of the edge. Multiplicity. Okay. No. You just imagine the edge got some number attached to it. Yeah. So when you pick the edge, the number comes with the x, so you sum all the numbers together. So we want to get a least number for minimum spanning tree. Right. Because I show you there are at least 2 ways to get the tree, right? So which these 2 ways you got the least number of sum? Okay. 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 How to do that? Yeah, how to do that? Okay. So let's go to the subject, how to do that. Okay, so I won't prove you why this, I will tell you two algorithms. I won't tell you why they can achieve it, but they are called the greedy algorithms. Okay, greedy algorithms meaning they make an optimal choices at each steps. Okay, each step they do, they pick the least one, but in the end, they still produce the least one. Okay, because this is not true for general cases. It doesn't mean that every step is minimal, implies that the whole process is minimal. Okay, in general, that's not true. Okay, but in this case, it is true. Every step, as long as you make sure you are minimal one, then the whole process will be optimal. So overall, you can pick the smallest one. Okay, so they are called a greedy algorithm. I won't prove it, so we will just tell you how to do it. Okay, so first is called the primes algorithm. Okay, so primes algorithm start with you pick one edge with the smallest weight first. Okay, so it's not any root you start with. You start with the edge with smallest weight. Okay, and then you successively add to the trees of minimum weight that are incident to the vertex. Okay, and then you keep doing that until you form a tree. Okay, let's show you the example. Okay, so let's say in this case here, you got this weighted graph. Okay, you got this weighted graph here. Okay, so which guy is the minimum weight? Huh? FB. Okay, FB, CD, or KL. Okay, so you just pick one of them to start with. Okay, in this case, they start with BF. Okay, they start with BF. And then you successively add the vertex that is, the edges that is incident to B and F, which has the minimal weight. Okay, so in this case, B, you got 3 and 2. Which one you pick? You pick 2. Okay. Here, F, you got 4, 2, 3. Which one you pick? 2. So you grow down here, grow down here. Okay, and then you keep growing on. Okay. So in the end, you got BF, and then you pick AB, and you pick FG, and then from A, there's only one to pick here is E, because if you pick here is 4, not good. So you pick the 3 one. And then if you pick here 2, you can go either here or here. Okay. But it choose to go here because you know that you don't want this. Otherwise, you need to go down from here. You get it or not? Okay. So you pick the you pick the minimum one. Okay. And then you keep doing it. And then you will sum up to be 24. This is the minimum one. So meaning if you start from CD, right, you also can reach this 24 wait. Do you want to try or not? Or you want to try also? Huh? You want to try? Yeah, try. Okay, let's try then. Okay, let's construct our own spanning tree. So let's start with CD, huh? Okay, let's start with CD. Okay. So CD, wait one. Okay, CD. So next, we can pick this one. Okay, we also can pick this. We also can pick this. Right. So which one you want to pick? CG, huh? Okay, let's say we put CG first. So let's draw out what we pick. So 2 is CG. CG is 2. Okay. So next, which one you want to pick? You want to pick here or here? I think both you can pick. Huh? GH. Okay. Let me see the algorithm. Yeah, okay. Huh? What? You can pick this, right? Let's say again. You uh-huh. Yeah. Later we will pick FG as well. I think so.
Yeah. Yeah, I think we will pick FG. Okay, so let's pick here. I try, maybe we'll go wrong, I don't know. Let's try 3. Okay. And then H I also can pick, right? H I can go triangle. Triangle. Or pick G first. Okay, so we can go to BF. BF. So GF is 3. Okay, next I can pick FB. So FB is 1. And then we can pick BA, right? Is 2. And what else? How about we start a new one? Okay. So 7, we can do what? Okay, already pick BA, right? Okay. And then we can do A, E, 2. FJ. Okay, do FJ. 2. IJ. JI is 1. Can do HL. HL. HL also can. L is okay. And so this is a tree, right? So it touches all the vertex and then there's no simple circuit. So this one is 1. So sum it up. Sum. Huh? 24. 24? Okay. 24, eh? Huh? 22? 22? Below there. Let me see. Did I copy wrong number or not? Huh? JI is 3, huh? I must copy wrong number. JI is 3. Any wrong number or not? This one is 3. Okay, this one is 3. 1 is 3. 1, 2, 3, 4, 5, 6, 7, 8. 8 times 3 is 24. Okay? Okay, good, very good. I didn't prove to you why it's true, but you have to produce the. Okay, okay, next. Huh? Say again. JK and KL. You mean you don't want to pick HL, but you pick JK? Yeah, it's the same. You see, replace the tree with this tree. Yeah. So as long as it's minimal at each step, you will somehow get the minimum. Okay, but I don't prove to you why it's true.
So it doesn't matter which way we go.
Yeah, it doesn't matter which way we go.
So if you turn out like you don't want to pick HL, but you turn out to pick HK, also works. If you don't pick this one, but you pick this, also works. Yeah. In the first edge, yeah. Start with the smallest one. Okay.
So you start with that, then all fine.
As long you start with that, and then next step you still need to pick the minimum one. For example, the next step here, you need to pick the minimum. Like these two, you must pick this one. You cannot pick this one because this one's already 3. And then here, how you decide whether you want 5 or not? You can go here by 3, but you go here by 5. So you must pick the 3 one. You cannot pick the 5 one. Okay. So this is how you decide which one. You need to decide the minimum. Okay. 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 Next one is called the second one. Is it the last one? Yes, last one. Okay. So the next one is called the Kruskal algorithm. Okay. This one also the same. You start with the smaller weight, okay, and then you successively add to the 3 edges of minimum weight. This one I don't care where the minimum weight is, but as long as you add the minimum one, okay. So you add all the edge of weight 1, weight 2, weight 3, and then keep going on. Okay. So you add the minimum one first, and then add until you got the spanning tree. Okay. Okay, let's see how it works. So the algorithm will stop when n-1 edge has been added. Remember just now we proved that a tree with n vertex has n-1 edges. Okay, so when you have n-1 edges, put it into an edge. You have to have. Okay, so how this works? So how this works is you start with a weighted tree. Okay, first you start with the least weight one. Okay, so you add CD and KL first. Okay, after you add CD and KL, let me make it more. So CD and KL. Next, you add one level up weight. Okay, level weight 2. So you can add this one. You can add only one here. Okay. Oh, here only one. I forgot here. Okay. Add this. Okay. Okay. Next, you can see that you still haven't formed. You haven't have enough edge yet from the tree. So add level 3 edges. Okay. So level 3, level 3, level 3, level 3. Here got problem. So you want to add here or add here? Up to you. Never mind, up to you. So he decide JK. You also can decide FG, but you cannot put both in. Why? If you put both in, what do you get? You get a circuit. Okay, you don't want circuit. So you only can get one. Okay, one of them. Either one of them work. So they pick JK. Okay. And then they also pick IJ. Yeah. Okay. And then have you formed the circuit yet? How many? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. 11, you got how many vertex? 12. So you can stop here. You don't need to add level. Wait for edges anymore. Because you already have a circuit. If you add wait for, you get circuit again. So you need a tree. Yeah. Oh, you mean the BF?
Yeah, so he doesn't choose FG because
It's just very.
FG is a
Let me see. He didn't pick. Okay, let's restart again. Then restart again. So here he picked BF, right? And then CD, right? And then KL, right? Okay. Then anything else? Okay. The next one he picked is CG, is level 2. Wait. Oh, sorry. 1, 2, 3. Okay, done. And then next is wet 3. So
you cannot choose FG already.
yeah, he got 2 MG. Yeah. Oh, okay. Okay, makes sense. Okay. Yeah. Yeah, makes sense. Okay. Okay. We got how many? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Okay. 11 edges for 11 vertex, 12 vertex. So you can see that this spanning tree looks like this, right? So let me try. But just now the spanning tree looks like this. Okay. But these two have the same weight, also have the same different minimum spanning tree with the same weight. Okay. So you can produce different minimum spanning tree but with the same weight. Okay. Two different algorithms will produce different minimum spanning tree. Okay. Okay. So okay. Done. Okay, done. Maybe let's take a break until 5:52 and then we will do quiz, tech quiz, and then we'll discuss tutorial.
变成可以。
Second.
哎，这里边更可以。有吗？无聊。
The meantime, you can come one by one select your quiz paper.
Discrete
然后用哪一个有两个步骤？一个是翻，一个是
是自然的。
乱。有两个步骤。这步骤是翻，翻的说没有你把最小一个 x 拿出来，然后把你的圆轴，然后剪一个。wait. 好，wait。OK，你要问，你的线离最短的路线是什么？这样子的那个最好都这个是最短的路线，这样子过来，这样过来。其实这个是反是的。不是我正常的，只是一直我。对对对。怎么有人对你加强？但是这个方法是，然后里面发表，压这样的，就这样。我应该是。这个是还有一个连法，就是你不用管那个 x 在哪里，就是你先决定一，然后然后它给放在帮你，它你要然后直到你也上到，直到你从头到尾。对，没错啊，也可以，但是你就可以问为什么可以，但是我没有告诉你。
如果你不做，你就像我这样的写不同的线。可以的，哎，刚才不是讲了吗？剩下你连下去会造成什么结果？第一连续的哦，你是说 B 不连？对，啊 B 不连 A 应该是可以吗？好，不一样。先这个除非你把 D 放去左边啊？为什么？因为这个应该说 at all edges incident，所以如果你先读 B 的话，你就要把所有生 B 找到啊。但是如果你读 D 先的话，你就可以先把它 OK 对，是这个，但是你讨论说对的。人家吵架了，人家吵架跟我讲一遍，问题是在
没关系，写在桌上。知道啊。
那个这个时候没有读。
有啊。哦，这是有。对对对。我有一个那个广告很久了，没有我的，没有两个人有，越来越有。也不对。那个水有资料，这个事情会没有找不到。我给他一直读嘞，开始到我。对，每个文章做点，然后如果是 cut 的话，在这里有点，已经有你了。回路赛种通路，但是他的那个确认有说把那个趴去除掉，不要是他的对哦，这个是一个好有啊。但是不可以这样套路。不要看，那个还有也是看你这个十分有没有人家点啊？开始。我看。好的，哦，好吧，我懂了，好，这样啊。 朋友都不能送给你。
啊，是啊，是，我也不会送给别人。
你老问你，我刚找问你呢。
这个，
哦，看到了。
你不要看，你不要看，你不要看。
不知道走的路。哦，
还有一天给他们。
好像有一本记得。最少一分钟。也不能给分。啊。
这个是毅力，这个是也，他们第一个不是先 traverse，
对，是第二步不一样吗？第二步，这是谁？
李佳明，
李佳明呢
看见他了。
？OK
出来。
OK，没事。
但是他第二步是就是
对
先前3个，第二步全部 step stop three 不就应该是前3个，那这个
哦，不是，因为你在 transfer left 上去的时候，你要重新做这个东西，重新跑那个程序，可以明白吗 ？OK， 你看啊，你 transfer 这个 left sub tree 的时候啊，对不对？你 transfer left sub tree 了，你要做的是，你还要再 visit 它的 root 先。
为什么要先？
啊，是这样的，它的那个 algorithm 是这样，就是你走，假如说啊，对，来看这个，你看，它那个只是我的总结罢了，你是最好要去看它的这个 definition 的哈。看我给这个 definition，你看，如果啊 T 只有一颗一个 vertex 的话，啊，就是它的 vertex，看你是很久的 B 很
9。
哦0.0+0，哦，你看朋友帮你拿，他看到你加入旁边。OK， 看，所以你只能够读 tree 只有一个点，才可以把这个点。那这个是什么意思呢？他是说，如果你的 tree 有 n 个 sub tree， 那你就要 start from 不然你觉得这个有问题是吧？那我们就直接去读这个。对，你看啊，你看，对 ，T R 点 R 是个T 个 sub tree right？ 然后你怎么读我的选择呢？那你就先 transverse T 一个，然后你再 visit 它的。
就是你2码之后一定要回去看第一的路，就是有 n 个 sub tree， 然后你 convert 一个 sub tree 的 left， 然后你就要回到它的 root，
没错。
然后就去看它的 right，
啊，对，没错。
然后就再看左边的，再回到2这里，这样。
还是要怎么应用？不然再看一个 post 的，再看一个 post 的。你看啊 post 的是说 ，OK， 只有一个点你就会读哦。怎么样呢？你 traverse T1 in post 的 traverse visit 那个 root，OK， 所以它意思是。对，先做哪一个？想做哪一个？
先做这个。
先做这个啊 ，OK。所以你看啊，in order 就是说，如果有一个点，它就是它哦；如果没有，你就要 transverse 这个先，OK。transverse 这个，你一定要 transverse 它的 left 先才去它的 root。
啊，对。
OK， 所以 transverse 它的 right 了，left 了才回去它的 root，然后再 transverse right，然后你 transfer 这个 left 了，再 transverse right，
我懂了，
可以吗？
我懂。
可以吗？可以吗？
可以。
那你是要做这个？
这个就是偏义，然后
transfer 它的 right，
然后到 right 就是
left， 然后再 left，
就是 B 的 right。
对 right， 然后才回去它的 right。然后你去了它的 left， 再去它的 right， 再回去它的 right。
就是因为 BCF 是这一整个的 subtree， 所以这个弄完了之后也出了。
Yes， 就去它的 right。
然
后它的 right 如果还有去的话，你就要 left 边 left 边。然后再回。啊？时候出。放错了，放错了。啊我。没有写步骤啊，这个没有写步骤，该写步骤。要。不然讨论一下这个，再看再聊。testing is everyone back here? Everyone back here? Everyone back here? Hello? Everyone back? Okay. Yeah, let's go. Okay, let's discuss, see whether you can get extra marks or not. Well, just now some of you still blur. So make sure you ask questions because just now some of them are from SWE. So make sure if you don't understand, you just raise. Then I will keep explaining again. Okay, don't keep to yourself. Where is it? Because I already discussed this with them last week, so we delay the midterm, so we also delay the quiz. Okay, please listen carefully, see whether you can get if I mark it wrong or not. Okay, so
So first one, okay, so this is first of all, this is a card game, okay, using the poker card. So this game is based on 5 card pattern that you can make, okay. So how many you can make it, then you will win with highest possibilities. The first question is how many combinations of picking 5 cards from the deck, okay. So when I pick this 5 card, I ask about combination. I don't care about permutation. So if you have different permutation, they are count as the same 5 card set, okay. So the answer is 52, choose 5, okay. Next, is about straight flush. Okay, so what's straight flush? Straight flush is 5 card sequential in rank with all being the same suit, okay. So there are only 10 possible sequence here. Okay. So how many suits do you have? You have 4 suits. Okay. So it's 4 times 10. Okay. Each sequence you have 4 possibility. So either you are diamond, club, heart, or spades. Okay. 4 times 10. And then next one is flush. Flush consists of 5 cards all being the same suit, not including straight flushes. So you need to use the inclusion exclusion principle to take away the straight flush. And then so all being the same, so is 13 choose 5. 13 choose 5 because and then you have 5, you have 4 suit, so you need to multiply by 4. 13 meaning you within the same suit you got how many cards? You have 13 ranks. So 13 ranks, either 5 of them will make up a 5 card with the same suit. Okay, 1.3. Any question? So if you manage to calculate half of it, I'll give you 1 mark. If you know how to take away 1.2, you also get 1 mark. Okay, see if you got mark or not. If you know how to compute the number of flush, including straight flush, I give you 1 mark. If you know how to take away, I give you 1 mark. Okay, try check. And then next, bonus mark. Bonus mark. So bonus mark got 3 questions hiding inside here. Because why I put bonus? Because I found that I put too many questions. So I just make it into bonus. Yeah. So okay. So bonus 1 is 4 of a kind. So 4 of a kind means all 4 cards of 1 available rank. Okay. So example is like 2, 2, 2, 2, and then mix with 1 random card. Okay. So actually it's 13. Okay, you have 13 ranks to pick here. Okay. And then times 48. Why? Because you already take away 4 cards. Okay. This one doesn't matter, this one. Okay. 13 times 48. Okay, next is full house. Full house is 2 plus 3. So what's 2 plus 3? A pair with a 3 of a kind. So I didn't explain 3 of a kind because I guess I want you to like see you can infer from 4 of a kind what is 3 of a kind. So 3 of a kind is 3 cards of 1 available rank. Okay. So it's 4 choose 3, and then pair 4 choose 2. Okay. So if there are 13 choices of 4 choose 3, then you left with 12 pair choices of pair. Okay. So for example, you get 3, 3, 3, 2, 2. Okay, this is a full house. 3, 3, 3, 2, 2. And then the next one is a straight consists of 5 cards sequential in rank. Okay. So, but with not all of them the same suit. Okay. So using the principle of inclusion and exclusion again, you take away the straight flush. Okay, because I don't want all of them with same suit. Okay. And then there are 10 possibility. and then each of them have 4 possible suit, so 4 to the power 5. And then take away the straight flush because I don't want them to have the same suit. Okay, so if you can get the minus the right number, I also will give you 1 mark. Okay. Any question on the first part here? Any question on this part? Any part that you want me to go through? I think few of you got my full marks here. For bonus, I mean. So bonus meaning you add up all your marks, you won't exceed 10. One full, we got my full marks. Fu Jingrui. Who is Jingrui? I think I remember this name. Oh, yeah. Yeah, you remember me. Fu Jingrui. Guo Zirui. Zirui, right? And then Jiang Fangling. Who is Jiang Fangling? Jiang Fangling. Oh, hello. Jiang Fangling. And then Liu Qianfu. Qianfu, Liu Qianfu. Oh, okay, yeah. Right. Tian Ye also got it. And then who else? Rainy also got it. Hey, Rainy full mark already. 565. Very good. 565. Okay. Yeah. Okay. Okay. No question. Next. Okay, next is about equivalence relation. So what kind of function or graph obey the reflexive property and why? So this one, I think I go through in the lecture notes. Okay, you should know about it. So the question, so I see that some of you confused with the R, real number, and the relation R. Okay, so one is a set, one is also a subset, but one is about relation, one is about real line. Okay, so don't use the wrong notation. And I think a lot of you draw this graph here. Okay, but if your set is discrete, this graph might look differently. Okay, so be careful on what you draw. So make sure you write the right graph and then draw the right graph. So the graph that obeys reflexive property, I put the answer as fx equal to x for every x in R. Okay, why? Because x and fx will form the relation. This is what we do in the class. So function can be understood as a relation because it is a subset of R cross R. Real cross real, not relation cross relation. Real cross real. Okay, so to obey reflexive property, what does it mean? For every element in the set, okay, x have to be in the relation. Okay, but we say that this term here is what? Every ordered pair here is actually equals to xfx. This is our relation. So every tuple have to write in this form. Okay. So this means these two have to equal. Okay. So when the ordered pairs are equal, x equal to x equal to fx. Okay. That's why we got the function fx equal to x. So if fx equal to different thing, if the for example, if we pick let me put what color? If we put fx equal to x squared, okay, then x squared doesn't satisfy x in R for all x in the real unless x equals plus minus 1 or 2. Plus 1 or 0. Okay, so this function doesn't satisfy reflexive property. Okay, because not all x, okay, not all x-axis in the graph. So for example, 2, 2 is not in the graph. Not in the relation. I get it now. I think I jumped some argument. I'm not sure you can get it or not. I jumped some argument here. Can you see that 2, 2 doesn't satisfy this equation? Can you see it? Can you see 2, 2 cannot satisfy this equation. So if you put s squared equals to 2, x equal to what? S squared equal to 2, x equal to square root 2. So square root 2, 2 is in the relation, but 2, 2 is not in the relation. Okay, this one clearer? Clearer or not? This one clearer? Okay. Because if you put square root 2 here, you get 2. Okay, but when you put 2 here, you get 4. So 2, 2 is not in the relation, but 2, 4 is in the relation. Okay? You get it? Get it? Get it? Get it? Huh? Okay. So this graph here is not reflexive. This is reflexive by this argument. Okay. Okay, next 2.2 open-ended question. Is human relationship reflexive, symmetry, and transitive? I don't know why your class put a lot birthday if their birthday is the same or what, something like that. Here the relationship just mean whether you know some person or yeah. Okay, but anyway, up to your definition. So my answer is okay. I can argue any way I like. So if I want to say human relationship is reflexive, okay, that means everyone know themselves. Okay, so human relationship is reflexive. If I say human relationship is not reflexive, okay, because not everyone know themselves well. Because someone doesn't know themselves. But I don't know whether you are true or not, but as long as you can argue the right way, I'll give you mark. Okay, as long as follow the definition of the reflexive, okay, symmetry. And then symmetry, I think quite a lot of person also say human relationship is reflexive because if I treat someone well, they will also treat me well. Yeah. Maybe someone not like maybe she experienced something bad. Yeah. So but if you believe in this way, you should keep believing. Okay. So yeah. And then next, also somebody say human relationship is not transitive. Okay. So how do you show that something is not transitive? So he said that if the husband is good with his wife is good with another guy, the husband may not be good with the guy. Okay, so it's not transitive. Okay, so you just need to give one counter example. Okay. Okay. Any question you want to go through? Any question that you want to go through? Okay, if not, you can start with your tutorial question. We will discuss it at 6:35. And then meanwhile, if you got any mark you want to add, you can come here.
这个一样
一样呢？
一样。
我看一下。
大城市的。
什么道理啊？
这个12乘13，你就是13是先选一条，然后是剩下12个再选一条。然后我这里就是13个里面直接填。
啊，对对对，OK，一样，OK，1分半哦，2分，2分。28，这个呢，你满了，加不了啊。OK OK，还要吗？好了，要给我，还给我。
这个
来
reflexive 的
对
证明，就是每个 F 是那个 F
啊，
对啊，
你没有解释，因为
啊，
你没有解释这个
F 还可以，
没有，你没有解释这一步。我可以给1分这个，但是你没有连到这个 reflexive definition。
就给1分，
好，就给
加1分就满。
好，可以。所以你明白吗？现在要解释，要用这个解释呀。你这一个还没有到这一步，你还没有解释到为什么。
要写这2步是相
对，就像我的步骤里面，可以吗？
我不太理解的，
对，你不太理解。
我不太理解这个是什么东西。
OK，你等一下啊，我先给他分一下啊。
是哪个是吧？你一共多少个？不加题。那就超过的话也没事儿，超过的话还是
可以超过你
超过了这个
没有？就要明年可以吗？
我不是很理解这个，
啊
就你到底怎么样才能
嗯
怎么样证明才是 reflexive？
哦，等一下，我给我看看啊。
没有，这个底下是我抄你的，
哦，OK，
只有这个是我自己写的。
OK，所以第一个你要知道这一个的定义是什么
，A B 画 B A，
？For every x in OK，你要用那个
A B A B A B， 就2个元素 A B。
对，我要写的是一个 set，你是说用 R 哈？你要用 R，OK，好，XRX，你要写的是这个东西
OK
你这个你要证明，OK，
嗯，
每一个都要这样，不是？所以你这一个你应该要把它表示成一个这样的东西先，你明白吗？比如说我这样子的话，我的意思是说，这个 for
这
every
个怎么证明？
对，这个怎么证明嘛，对不对？所以你看，这个的意思是说，我的方向长这样，我的意思是说这样，OK，可以吗？对，但是呢，只要我把 fx 设成 x，它就符合了，这2句话就对了，就对上了，听明白？这个 imply 这个 if fx
我想问一下
等于 x
这里的这个 R 是什么意思？是
啊，对
relationship？
不是，对，这个就是我刚才说的东西。这个 R 是这个 both R，你看这个有一条线，这个没有线，所以这个是 real
实数。
呀。如果你要换去不同的 set 也可以的，没问题的。
这个我没有。
但是重点是你要让这一个东西让它等于它，这样你就会符合这个条件，听明白吗？因为现在的这个 fs 可以是任何的东西，它可以任何的 graph， 但是你看我如果设不对的 graph，我就没有这个条件了，对吗？听明白吗？所以我一定要把这个 fs 设成 x， 我才可以有这个。
所以这个问题是怎样的
function 可以符合这个条件？所以我的 function 是这样，怎样的 function 可以符合这个条件？当 fx 等于 x for all x 的时候就可以符合。
对，那个 reflexive 不是如果是 A B， 然后也满足 B A 的话，它就是 reflexive。
这是 symmetry 吧？
这 symmetry。reflexive 不是自己和
自己和自己
相等。
这个是 reflexive if A B then B。
那这个但是这个的话，它不是 symmetric 吗？
你这是 A B B C 耶，
A B B C 是
我
sensitive
我是为了证明它不是我这写错了，这应该不是这个但是是这个
啊
我证明是这个不是 A 和 B 是朋友的话，B 和 A 肯定就是朋友
对，
所以我这个是想反证明它 sensitive 是不对的
对，你这个是全
我写错了，
对对对
，OK，
对，
那我交了
，OK 好，对，
这样我写前面这个
写前面这个，OK OK OK，就这个罢了哈，OK 好，
下面这个
这个
前面这边半对了，可是后面我又加了，
你加还是什么？
因为我一考试的时候我以为是太紧张，我要换位置，它是不是两个不一样？可是乘除乘的话没有差，
你说你乘2
没有乘2的概念哦，可是我考试的时候
这样就不能算错，算错了，还有OK， 等下我记一下，不能算错了，这个就是算错了，
咱们分析
，OK，
这个我的 explanation 虽然是有的，
这个
它是知道一样的东西，
我知道一样的东西，但是对，但是等一下我先解释一下它来，但是你没有连上来诶，
就是是两个东西是一样的，它的那个
为什么两个东西不一样？
因为它是 reflexive 的话就是它会反射，现在两个东西是一样的。
但是问题是它不是那么直接来说，你听得懂我刚才解释的东西吗？reflexive property 是什么？
两个东西是这样，
不是，就是自己和自己要活在那个 relation 里面，我每一个 element 自己和自己要活在那个 relation。For function 呢，它的 relation 长成这样，OK， 所以你要怎么让它符合这个条件，你就让 f(x) 等于所有的 x。OK， 可以，等下我看一下，就是你这个是你的 relation， 然后你要符合这个条件，要讲让这个 relation 符合这个条件，你只要让这一个等于这一个 for O(x)， 你要符合这个条件，对吗？OK， 你是哪里人啊？美国人，哪里人不一样？
确实是
确实 OK， 加一分。
最高的这种
这道题这个最高，太好了。
然后比如说这边有1分，然后这个是1分嘛，那我这个写错这边是对的。
可以的，加一分。
这边，然后对面它是那个。
那个我读清楚的。OK， 可以。但是你这个有一个写不好的地方，就是你这个 y， 我其实也是可以啊，就是这样写的。然后最好以后用 f(x) 比较好。
OK， 那你先加小加加。
还有一个东西再跟你讲一下，这个要让所有的 x 对 ，OK， 不可以一些对吧？一些对就变成这个情况这个情况我们不要，不可以一些对，要所有对。
这个也没有写
所以你就没有写我就告诉你要写OK， 记得吗？我们第一次学 proposition 的时候。1、2、3、4
对。
OK， 好，可以。没有做 bonus。
没来得及，因为这题想了很久，当时在想，因为我以为它是那个，它顺序不是一样的。
OK，
是40。
你写错这个。
这个写错了。
这是什么
？4800。
4800，哇！
因为我当时想的是说它的顺序是不一样的，所以它就会就在这里。
好，
这个地方
OK 好，对，没了。好，对，等一下我看一下啊。OK，我查一下我徐佳琪对吧
235。
？10啊。OK，好，来，这样，别放了，
这个直接这个直接
来，
你讲
啊，有看见？
那 graphic 能够这样。
没有，这个总分分。
那边可以。
谁扣分？
什么？我看一下。啊，你这个，
等下我明白观察去，
啊，你明白什么？
我不能讲表达。
嘿，至少你要来，不是你这个，你知道有什么问题吗？这个我要全部对哦，不可以只对给一个点嘛。
啊，
对啊，每一个点都要对。
let's say 嘛，
那
其中一个点，
一个点不够，我要所有点对。
多少那个这个
啊啊啊啊！你一定要对给所有的点，不可以一个点对吧？可以吗？
可是你已经有放置点，
你一定要对给所有的点。如果你这边写所有点，我就可以给一分。所有点要对，不可以一个点对吧？一个点对就是这个，你看一个点对，可是它有点不对，这样就不可以。我要所有的点都要对。
啊，这是一层。
等一下我看一下，
看前面的，
前面是错的，把它剪对了。
你怎么这样神奇了呢？
我想太多了那时候。
可是你这么忽然间会想到这个东西，这么这个不是对，但是这个剪的这个东西就是这个东西来哦。
是吗？
对啊，
小心他把这个搬出来，在这边啊，把等下他剪到不一样的东西，可是他刚想对了。
我考试紧张，
刚巧对了，
我定了，
好啦，给你一分
2分
啊，刚好对啊，真的是刚好诶，刚好。
跟这里也加1分啊，因为我这边做对了。
对。
这里，如果你把这一个搬上来，你就对了。
如果你这个是剪不成的话，你就可以拿一分。
然后
没有，如果你这个没有写，这个就
对。
可是我明白这个，
这样
是咯。
哦，来，那时候我想太多，我就
然后你怎样可以忽然间跑出这个东西？
这想来52种考，你每个选一个，选一个，选一个，
哦，
还有10种样子。
但是你这个就会选太多啊，你可能要抽几个
啊，
太多了这样。OK 那我给你一分啊。992。
1分，对，
下次啦，下次还有一次
下次啊
机会，还有一次机会，还有一次机会。
5分就是多少分？
28分。
到时候分给他们，我的朋友快，没有用到。
要这样讲，
对。
忘了。
对。
1小时。
马来历史，
呀，这样1.3，1.3做过，然后你算对一半哈。OK，还有吗？没了。OK，好。2600，还要？有啊。OK。
对啊。
哎，我是不是上次有问过你这个问题？你是从数学转过来？是我上次有问过你，好像有问你。哦，所以是这么转过来，太难了。OK，可是这一门你有学过吗？这一门你是不是有学过啊？
有啊。
有啦，比较多东西啊，比较复杂还是怎样？你学几年？你几时一个 Sam？OK，
老师不要忘记我 tutorial。
你的会，我会的。第几题了啊？9点多啊，我现在就开始讲。9点。
在第10章，第10章的第2部分。
是在那第二部分，是在第二部分。
为什么不给我们看？
第十，这是第十。12、11、12，然后第二 ，OK， 找到了 ，OK， 好，我现在开始讲。哎，怎样？还要加分
对，想象
？OK，
就这个是就是哪？
啊，OK，对。
直接给你就可以了。
OK，可以直接给我，可以，没问题。Hello, let's start discussing. So, you can still continue to do if you want, because I will start to discuss week 10, 9.6.2b first. Question from one of your classmates. Okay, so given this partial ordering here, okay, so my answer here says that this is a partial order, but 你叫什么名啊？报上名来啊？林一鹏？什么？什么声音？我没有听清楚。我没有。一凡啊，林一凡，OK 好。于一凡 ，OK。Okay, your classmate Ifan asked about why is this partial ordering? In particular, why is this transitive? Okay, so why is this transitive? So for transitive, what's the definition? You should recall the definition. If AB, BC, the relation, then AC have to be in the relation for all A and B in the set. Okay. So your set is this, in this case, okay? So you need to check for all elements that satisfy this condition first. For example, what? For example, 0, 2, 0, 0, 0. Okay. And then 2, 2, 2, 0. Okay. Or 2, 2, 2, 3. And then 2, 3, 3, 3. I think that's all. Okay. And then you need to show that AC is also in the relation. Okay, let's say we take one example. If 2, 0, 0, 0 is in the relation, is 2, 0 in the relation? Yes. Okay. If 2, 2 is in the relation, 2, 0 is in the relation, is 2, 0 in the relation? Yes, this one. And then you need to check for all. I think all of them in the relation. 2, 3, 3, 3 is 2, 3 in the relation? Yes, it's 2, 3. Okay. Okay. Yeah. Okay. That's all for this one. Any question from previous? No? Okay. Last week, because we didn't discuss the tutorial, I hope you do it at home. If not, we will discuss it in the next week. But there's one additional question I discussed with them. Maybe I should talk to you now. Okay. Last week, I add this additional question in here. So what question is this? Let me. Okay. So last time, remember we solved a 7 bridge of Königsberg. Okay. The Euler part. So now I also got a modern 7 bridge in Putrajaya. Okay. So Putrajaya is a government administration center in Malaysia. So it has a nice garden which you can go to. It's about, I think, 20 minutes drive from here. Okay, you can go to Putrajaya. So Putrajaya is this island here. Okay. And then there's 7 bridge that connects to Putrajaya. Okay. This one I searched from Google Map one. So 7 bridge. So you got 1, 2, bigger, 3, 4, 5, 6, 7.
Okay. So 7 bridge of Putrajaya. So the question is, can you have a Euler circuit? Huh? Oh, so fast. Why don't you have a Euler circuit? Huh? Why don't you have a Euler circuit? Okay. So how to answer this question? So do you have an Euler circuit? Or Euler path? Euler circuit or Euler path? So how many vertex you have? 7 vertex? Vertex. How many vertex you have? Huh? 8? How many vertex? So here can string to 1 point. Okay. Outside here is also connected. 2. You only got 2 vertex. Okay. So either is Putrajaya or outside Putrajaya. Okay. Because outside Putrajaya is connected. So you can string all these points into 1. Okay. So you can string the length into 1 dot. Okay. And then draw edges when they are connected. Okay. Remember from last time the dual graph. Okay. So how many bridge between Putrajaya and outside Putrajaya? 7. So you got 7 edges. Okay. So you got 7 edges. 1, 2, 3, 4, 5, 6, 7. So do you have an Euler circuit? Why? What's the theorem for Euler circuit? All vertex have even degree. Okay. So your vertex got how many degree? 7. Okay, which is odd. So there's no Euler circuit. How about Euler path? Huh? Why? The theorem says if you have an Euler path, which is not an Euler circuit, it can only if the vertex you have how many? Exactly 2 vertex of odd degree. Okay, so there are 2 vertex with degree 7, which is odd. So you have an Euler path. So that means if you start from Putrajaya and then you try to walk, you have a walk of all the bridge exactly 1, then you will end up outside Putrajaya. Okay? And if you start outside Putrajaya and walk through all the path, all the bridge once, you will end up inside Putrajaya. Okay, this is the Euler path. Okay, makes sense? Okay. Okay. Next. Next. What's the question for today? Okay. So today, I think the question mostly is about planar graph and what did we learn last week? Planar graph. What else? Yeah, planar graph, and then Euler formula, then graph coloring. Okay, good. Okay, so 10.6 asks you whether it's planar or not, I think. So you just try to draw a planar representation for your graph such that there is no edge crossing. You can draw a different one than mine, but as long as they are isomorphic, it's fine. So try to move around. Move the. On this graph, although you have a edge crossing here, but as long as you can draw an isomorphic graph which has no edge crossing, then it is a planar graph. Okay, as long as it admits a planar representation. Got it? Okay. Please feel free to stop me. Okay, 10.7.8. Okay, want to show it is non-planar. Okay, in the class we already described a few methods to show it. One is to find a subgraph which is homeomorphic to K33 or K5. Okay, K33 is the complete bipartite graph between 3 vertices, and then K55 is the complete graph with 5 vertices. So in this case, I can find the K33. Okay, so I draw this white and blue to tell you that this is a bipartite graph. Okay, so this is the K33 subgraph homeomorphic to K33. So it is non-planar. Otherwise, you can use the one of the corollary, use the contrapositive of one of the corollary to prove it. Okay, you also can do this computation here. E is greater than 2v minus 4. E is greater than 2v minus 4. You also can use this. Third, you can use the diagrammatic method. Okay, try to draw some isomorphic graph. Okay, try to move it around. You see, try to move this around, and then you see that if you try to move any 1, 2, 3, 4 of the vertex into different region, you can't avoid edge crossing. This one is more complicated, so you need to try yourself. Okay, so if you put C inside here, then you will have edge crossing here. If you put C inside here, then you will have edge crossing somewhere else. Okay, so you have to argue. No matter how you put this 4 vertex in any region, you won't remove the edge crossing. Okay? Okay, because these 4 are symmetry, you just need to discuss one of them is enough. Okay, because what they are symmetry. Okay, so this one is harder. So easier you use the Kuratowski theorem, the homeomorphic. Remember the topology we talked about last time. You should go and revise. Okay, Kuratowski theorem, and then the corollary we talk about the 3 corollary after the Euler formula. Okay. 10.7.11. This one K5. Last time we only used the corollary to prove it. Now we want to use the diagrammatic method to prove it. So similarly, try to draw some isomorphic graph and then try to move this A somewhere else. Okay. So if you move this or move this is symmetry, so you need to discuss one of them is enough. Okay. So verify that if you put here, you got edge crossing. If you put here, you also have edge crossing. If you put here, you also have edge crossing. If you put here, R3 also have edge crossing. So there are only 1, 2, 3, 4 regions that you need to try. The vertex A here. Okay. 10.7.12.14, just use of the formula. I think no need to go through this. Just use the formula. 10.7.18 is a proof question. So you got K connected components. Okay, so K connected components. So they are not connected. So K. So you got K graph. Okay, 1, 2 up to K graph. So you want to get a formula that connects R, E, V, and K. Okay, how to do that? So here you can. There's one technique here is to add one edge between them. Okay, so that they form another planar graph, right? Make sense? So for example, like you got this graph here, then you got this graph here, then you got this graph here. Okay. So if you join them together, they become a big planar graph. Okay. So in this way, you can use the Euler formula to all of them again. Okay, make sense? Make sense? Huh? Make sense? Yeah. So you got K component, and then you add edges to connect the connected component to become a big planar graph. Okay. 10.8.20. Okay. The question asks whether this is homeomorphic to K33 or not. Okay. So it is not because this is planar actually. Okay. Maybe you can see from the degree of the vertex, but if you can see from planar, gritty is faster because you can just move this line here. Yeah. So it's planar. K33 is not planar. So planar cannot isomorphic. Okay. Next. What's the next one? What's this question? Anyone know one marks? Oh, this one also asks about planar, non-planarity. So it's not planar because it contains a subgraph that is homeomorphic to K33. Actually, the whole graph is isomorphic to K33. So this is non-planar because you have a subgraph that is isomorphic, homeomorphic to K33. 10.7.24. They give you this graph here, asking you whether it is planar or not. Looks like some cloud. Okay, it is not planar because it contains the subgraph that is homeomorphic to K5. So I cross talk here. Cross talk here. This is non-planar. Okay, then now we go to the chromatic number of a graph. So if you want to color the graph, it is the same as coloring the dual graph. Coloring the map is the same as coloring the dual graph. Okay. So you make the connected part into a point. String a connected part into a point. String a connected part into a point. Connected part into a point. And then join them if they share the same boundary. Okay. So you can see that the chromatic number is 2. Because you can use 2 color to color the graph, and then if it is less than 2, then yeah, it has to be greater or equal to 2 because there's at least 2 vertex are connected. Okay. Because you need to measure these two have the different color, so it's greater or equal to 2. Less than 2 because you can color the graph with just 2 numbers. Similarly for 10.8.4, so you string the connected component into a dot, and then you join them if they share the boundary component. Okay. So you can use the same argument to show that chromatic number is equal to 2. Okay, now this one, there's one tips here. So if you try to color this graph, 3 color is enough. So the chromatic number is less than or equal to 3. But how do you show that the chromatic number is have to be greater or equal to 3? Okay, why? Because you have a triangle. So for triangle, you must have at least 3 different color, right? Because you need to measure these 3 vertex has the different color because they are all adjacent to each other. Okay, so that's why you have at least greater or equal to 3. 10.8.8 is the same, so let's skip this. 4, yeah, for the 4 case. So in this case here, you see that 4 is enough to color the graph, so the chromatic number is less than or equal to 4. But why the chromatic number is greater or equal to 4? Okay, how to show that? How to show that? Because it contains the complete graph of K4. Right? Because it contains a complete graph of K4. So in K4, all the 4 vertex are adjacent to each other. So all these 4 vertex needs to have different color. Okay, you can see that actually these 4 numbers also occur at this subgraph here, right? So can you see the correlation between? Okay, so why I need to add this extra color here? Exactly because these four are connected. Yeah, otherwise I can reduce my chromatic. Okay. Yeah. So actually this subgraph is causing the problem. Okay. I think 8.16 you can go back and try and read. This one is an argument to say that if your circuit has odd, I think this one is to show that what? Yeah, this one is, for example, to show that pi chromatic number of Cn is 3. That cannot, it's 3. If, let me see, what's this one? So remember a circuit with so Cn CNN is what? Or I should say is not equal to 2. Yeah. So this question is actually asking about showing that chromatic number of circle or circuit with n equal to odd is not 2. Okay. But I think in the tutorial question or in the lecture notes, the textbook example, they say that it is 3. Okay. So this one shows that it's not 2. So if it is not 2, and then if it is less than 3, less than or equal to 3, then definitely it is not 1, so it has to be 3. Is it okay? This is also one way to show that pi of Cn is 3. Yeah. So if pi Cn not equal to 2, not equal to 1, and pi Cn equal to 3, then pi Cn is equal to, sorry, this one is less. Okay. Less than equal to 3 got how many number? Got 1, 2, or 3, right? So if it is not 1, if it is not 2, then it must be 3. Okay. So why is it not 2? So you just go through this argument here. So the argument here will be saying that, let's say we can color with 2, okay? But if you write out the vertex order V1, V2, V3, Vn, and V1, so you will have blue, red, and then you will stop at blue. Because when it is odd, it always blue. Okay. But the last one is V1, blue. Okay, blue, then adjacent vertex cannot have the same color. So contradiction. Accept at least true. Okay. If no more, please hand me back your quiz before you leave. Okay. And next week, please be prepared.
呀，怎么证明那个四舍五入啊？很难哦。
我看到有个说法说它的是 K5
啊？有看一下，哪一个？哪一个？
地图肯定的，
哦，呀，怎么变成 K5啊？
它变成 K5 肯定成 K5，为什么都变了？
怎么变 K5？
这是我不知道。
哎，等下，你给我看一下。所以这个有1分，这个有1分，给你1分了。哦，
用照名字啊？
啊，不用。这个错对吗？这错啊？错。4乘13就是
没有程序。哦，哎呀呀，对对对，OK OK OK，可以可以可以。这个13乘48，哎，也对。这个呢，12乘13，4除2是6啊。哎，你这6跟4怎么来啊？
对。
哎，下次要把这个步骤写出来呢。
有5个区域2
啊？可以啊。
能够有5个区域，
然后
每两区域都相邻，这也对情况下
对啊，都对。后面没啊？
所以说也就是要证明，反正5个区域
好，
都要
也对嘛，
就5个点
来给大家
配伍，
240，
就是要证明
所以2、3、4这边4分，
里面
6分。对，OK，吃饭。对，
这个叫
啊，这个怎么样
他们这个 P 是代表什么？
？P 是一个 proposition。
那 proposition 是哪一个？
随便任意啊，任意。
那这个解释是怎么理解？
这个解释就是说，如果我让这个 proposition 是这一句的话，对不对？
x 等于0是
对
proposition，
x 等于0是 proposition， 对。There exists an x for every y， 这个是对的嘛？那你只要选 x 等于0就好了，来任意。他这里说 for every x there exists y，x 是等于0。不可能全部 x 它都对嘛？只有 x 等于0哦，对。
那我就随便命名一个就可以，给 proposition 随便写一个。
如果你要证明这个东西是错的，你只要找一个 proposition 就好。
这个问题
呀，
是不是可以看成就是要这样，在一个平面上5个区域相邻，两相邻
5个区域相
没有5个区域，不可能有5个区域两相邻，这样因为5个区域如果它两相邻就要5种
5个区域两相邻就要有2个原则，5个区域两相邻。OK， 然后
把它抽象成那个就是 K，
抽象成
就是每个区域都变成一个点。
哦 ，OK，
这就变成 K5， 然后接下来就是要证明 K5。
我不是之前跟我们证过啊？
对，那是不是就说明4个问题就证出来了？它不是平面图，所以平面上不可能存在5个区域两相邻，所以最多是4个区域两相邻，所以只要4个。
是这样证的，
是吗？
是吗？我没有看过，好像。要不要直接搜一下？我看看，感觉好像挺有道理。
啊，那段论证那段，我觉得看着怪怪的。
哪一个？
就是你当时说。